Jai Hind, welcome to the course Network Analysis and Synthesis, and today I am going to discuss about the pole and zeros. So what are the learning objectives of today lecture? First we will discuss what is pole and zeros, then what is the significance of poles and zeros, and so under the pole zero concept we will cover definition of the pole and zero and significance of pole and zero. Then once we define the pole and zero, we can understand where we get these pole and zeros. So basically poles and zeros are present in network functions. So network functions are basically of two types: driving point immitance function and transfer function. So under this heading we will discuss what is driving point immitance function and what are their properties. Properties means what are the necessary conditions? What are the necessary conditions for a network function either to be a driving point immitance function or transfer function. Okay, so under the properties of transfer function and driving point, network function is given and you are required to find out whether the given network function is driving point or not. So that will be decided by, there are certain conditions, or you can say restrictions on the location of poles and zeros in S-plane. So property means what are the necessary conditions or restrictions on the location of poles and zeros in S-plane. So under this we will cover all the conditions for a network function to be a driving point immitance function or transfer function. Then using the pole zero plot we can find out the sinusoidal response. So this will cover under this sinusoidal response, or you can say the steady state response from the pole zero locations, and the last is the time response from the pole zero plot. So a network function is given and you are required to find the time response. So how we will get it using the pole zero plot, that will cover under the this time response from the pole zero plot. So take one by one. So first we go for the pole zero concept. So any network function is given in the form of polynomials. So this is the polynomial form, polynomial in S. Okay. So ns upon ds, this is the numerator polynomial and this is the denominator polynomials. So a function is given in form of the polynomials, or a network is given and we are required to find the network functions. So once the network function is given in the form of the polynomial, and what are these coefficients bm, bm minus 1, b1 and b0, similarly an minus 1, an minus 2, a1 and a0, these are the coefficients and they are real and positive for a network containing passive elements only. So if the networks are containing the passive elements, we get a0, a1, an, b0, b1, bn as a real and positive. So we can see that the degree of the numerator polynomial is m, okay, and the degree of the denominator polynomial is n. So if we equate if we equate ns is equal to 0, ns is equal to 0, it means polynomial becomes equation. So, and we find the roots of this equation, we get m roots. So, if the degree of the numerator polynomial is m, if you equate to 0 and find the roots, so there will be m roots, say z1, z2, zm. So, these are the roots. These are the roots of ns is equal to 0. Okay. Similarly, degree of denominator polynomial is n. We can see here. And if we equate ds is equal to 0, we can get n roots and say these roots are p1, p2, pn. Hence, the above equation can be written in terms of this. We can write in this format, s minus 0. So, these are the roots of numerator and these are the roots of the denominator polynomial. Okay. Once we equate equal to 0. So, what is h? H is a constant known as a scale factor and it is given by ratio of bm to an. Bm to, this is your bm and this is the an. And z1, z2, zm and p1, p2, pn are called complex frequencies. Why they are called complex frequencies? Because this s is a complex frequency. S is a complex frequency. S is a complex frequency. So if we subtract something, that is also a complex frequency. Similarly, P1 is also a complex frequency. So when the variable s, look at this line, has value equal to any of the roots, say j1, z2, z3, zm, what will happen? If s is equal to z1, so this term will be 0, this term will be 0. If s is equal to z2, this term will be 0 and similarly. So any value of z1 is equal to s, then the numerator will be 0. So this function fs becomes 0. This fs becomes 0. So what does it mean? It means when the value of roots z1, z2, z3, any one of them are is equal to the s, then the fs becomes 0. So this z1, z2, zm, they are called the zeros of fs. So what are the zeros? Zeros are those complex frequencies at which network function fs becomes 0. Okay. Similarly, when the variable s has value equal to any of the roots p1, p2, pn, if s is equal to p1 or s is equal to p2 or s is equal to p3, then this becomes denominator becomes 0 and fs becomes infinite. So fs becomes infinite. So what are the p1, p2, p3? They are called the poles of fs. So what are the poles? Poles are those complex frequencies at which network function becomes infinite. So we have defined what is pole, what is zero. Basically poles and zero, they are the complex frequencies, and the zeros are those complex frequencies at which the network function fs becomes 0, and poles are those complex frequencies at which network function fs becomes infinite. Now what is the significance of pole and zero? Suppose any network function is given in the form of the polynomial. We can write the previous equation here. Bm s to the power m, bm minus 1 s to the power m minus 1 plus Bm minus 2, this is minus 1, okay, s to the power m minus 2 plus b1s b0 upon an s to the power n plus an minus 1 s to the power n minus 1 plus say a1s and a0. So if you are required to carry out the time response of this function fs, what we do in the previous lecture we discussed, we carry out the partial fraction expansion. So carry out the partial fraction expansion, we can write this. So what we'll do, after this we write in the pole 0, then we write the pole 0 format, pole 0 form. So and then the carry out the partial fraction expansion. So ns upon ds can be written as k1 upon s plus p1, k2 by s plus p2, k3 by s plus p3, kn by s plus pn. If we take the time response, so it is k1 e to the power minus p1t, k2 e to the power minus p2t, and kn e to the power minus pnt. So look at here. This is the pole. These are the poles. Pole. So we can see that poles of a network function determines time behavior of the response. It determines the time behavior. So whether the response will be like this, response will be like this, or response will be like this, that will be decided by these poles. And what is role of the zeros? Zeros decide the magnitude of the response. So hence poles determine the time variation of the response, whereas the zero determine the magnitude of the coefficient k1, k2, k3. So these are the roles of poles and zeros in a network function. Poles determine the time variation, whereas zeros determine the magnitude of coefficients k1, k2. What are the k1, k2, k3, kn? They are the poles residuals. So let us examine the significance of pole and zero at the origin. Okay. If the pole is present at the origin, so we know that dividing a given function fs by s corresponding to integrating the inverse ft. So we earlier lecture we had defined 1 by s is a integrator. 1 by s, how will get 1 by s? When there is a pole at origin. And suppose if the 0 is at origin, so 0 is a differentiator. 0 at a origin differentiator. Integrator and differentiator. So s is a differential operator and 1 by s is a integral operator. So what we can conclude, system function of a differentiator must have a 0 at the origin and integrator must have a pole at the origin. So this is the significance of poles and zeros. Now come to the network function. So what is network function? It is a transform function relating current and voltages at the different part of a network. They are called the network function. So they are defined for the one port network. One port means one pair of terminals. So suppose this is your I1 in transfer, this is your V1, this is plus, this is minus. So one port means one pair of terminal. So network function for one port network, they are ZS. ZS is the ratio of Vs upon Is. Basically it is impedance function. And Ys is Is upon Vs. This is the admittance function. So for a one port network, there are two network functions, ZS and Ys, and they are defined in this way. Network function for two port networks. Two port networks means where are the two pair of terminals. So say this is your I1S, this is your V1S plus minus here, this is your I2S, and this is your V2S. So how many network functions are possible for a two-port network? So let us see. So first one is the Z11S. Z11S is nothing but it is the ratio of V1S upon I1S, and Y11S is I1S upon V1S. Similarly, at this port, output port, we can have the two network functions Z22 and Y22. So Z22 is the ratio of V2S upon I2S, and Y22S is the ratio of I2S upon V2S. So these are the driving point immitance function for a two port network. This is the driving point immitance function. Immitance means impedance, either impedance or admittance. So there are four types of driving point immitance function for a two port network. So how many there? There are 6. 2 for the one port network and 4 for the two port network. Now come to the transfer function. So what is transfer function? It is defined as the ratio of Laplace transform of the output to the Laplace transform of the input under the assumption that all initial conditions are set to 0. So this is the definition. So it is used to describe network which has at least 2 ports and relates the transform of one quantity at one port to the transform of another quantity at another port. So a network function to be a transfer function, the port must be, at least there must be 2 port. Network function, transfer function does not exist for one port network. That is the moral of the this story. So transfer impedance. So transfer impedance is Z21S. So it is impedance. So it is the ratio of voltage to current, and voltage of which port? Voltage of port 2, output port, and current of input port. So here 2 and 1 is written in the order of effect and cause. So here this is your output, that is the effect, and this is your input, that is the input or cause, output or effect. So this is written in this order. In some books we can find, you can find Z12S. So Z12S is basically V2S upon I1S, because transfer function is defined as the ratio of Laplace transform of the output to the Laplace transform of the input under the assumption that all initial conditions are set to 0. Transfer admittance Y21S I2 upon V1. Voltage transfer ratio V2S upon, so this is the voltage of output port, this is the voltage of input port. Current transfer ratio, that is the alpha 21S I2S upon I1S. So we can see that in all 4 variables, the numerator polynomial is of output port. Numerator variables is of output port. V2S, I2S. Okay. How will get the network functions? What are the procedure to find the network function? So any network is given. Write the equilibrium equations for various voltage and currents, because the network function is is a transfer function relating current and voltage at the different part of the network. So write the equilibrium equations for various voltage and currents. Then after writing the equations, what we do, we apply the Laplace transform just to convert the, if there is differential equation into the algebraic equations. And so, and setting all initial conditions to 0. We can see that suppose there is an inductor, suppose in the circuit there is an inductor. If we write a for VLT, if we write the voltage equation, this is your IT. So VLT is L dit upon dt. So if you take the Laplace transform VLS, it is coming SL IS minus L I0. So to find the transfer function, equate this term. This is equal to 0. Equal to 0. Why? Because it is all initial conditions are set to 0. Okay. Then once we take the Laplace transform, the equation it becomes a algebraic equations, and algebraic equations can be solved by algebraic manipulations. Then we take the ratio of the excitation, ratio of the transform response transform to the excitation, or output to the input. Now we are going to discuss what are the necessary conditions for a network function to be driving point functions, or we can say what are the restrictions on the location of poles and zeros. So a network function is, if a network function is given, so the first is this, all the coefficients must be real and positive. A0, A1, A2, A3 up to AN, B0, B1, B2, B3, Bm, all coefficients must be real and positive. That is the first property or first condition. Second is poles and zeros, if complex or imaginary, must occur in conjugate pairs. This is the second properties. Then the real part of all poles and zero must be either negative or 0. Negative means suppose we are getting one pole, suppose this is coming minus sigma 1 plus j omega 1. Okay. So this must be either 0 or negative. If real part of any pole or 0 is 0, then that pole or 0 must be simple. Simple means distinct. At that location there must be only one pole or 0. This is the fourth property. Fifth one is the polynomials ns and ds cannot have missing terms between those of highest and lowest degree unless all even or odd order terms are missing. So ns and ds, highest degree, suppose ns is m and lowest is 0. So there should not be any missing terms, provided the function is either even or odd. Similarly for ds, so from the n bms to the power en s to the power n, 2s and n minus 1, s to the power n minus 2, there should not be any missing terms, okay, unless the function is even or odd. So this is the fifth property. Highest degree of ns and ds may differ in degree by 1 at the most. So degree of this numerator polynomial and denominator polynomial may differ by 1. The lowest degree of ns and ds may differ by 0 or 1. So degree of the numerator polynomial is m and degree of the denominator polynomial is n. So m minus n can be 1, okay, at the most. So these are the properties of driving point immitance function, zs or ys. So if a network function is given and you are required to find whether it is driving point, so we have to check all these conditions, all these properties you have to check. any one of the property is not satisfied, then the network function is not a driving point immitance function. Similarly, we can have some property for a network function to be a transfer function. So coefficients in polynomial ns and ds of fs must be real and those for ds must be positive. What does it mean? It means all the coefficients of ds must be real and positive, whereas in some of the coefficients of ns may be negative. It means, but for ds coefficients must be real and positive. Poles and zeros, if complex or imaginary, must occur in conjugate pairs. Clear? The real part of poles must be either 0 or negative. There are two parts of condition third, and if the real part is 0, then that pole must be simple or distinct. Means at one location there must be only one pole. There should not be multiple poles. The polynomials ds may not have missing terms between those of highest and lowest degree unless all even or odd order terms are missing. Same as we discussed in case of the driving point immitance function. The polynomial ns may have missing terms between those of the highest and lowest degree, and some of the coefficients may be negative. The degree of ns may be as small as 0 independent of the degree of ds. So these are some differences between we can have this and this, because ds may not have missing terms between those of an highest degree and lowest degree, whereas in case of the ns it may have some missing terms. So for G2S, so this is the voltage transfer ratio, this is the current transfer ratio. The maximum degree of ns is the degree of ds. So degree of ns and ds must be same in case of G21S. G21S is the voltage transform ratio and alpha 21S is the current transform ratio. And for Z21S and Y21S, the maximum degree of ns equals the degree of ds plus 1. So there are four, basically they are the transfer functions. So in case of G21S and alpha 21S, degree must be same. In case of Z21S and Y21S, degree of ns equals the degree of ds plus 1, higher 1 degree. Okay. So these are the some properties for a transfer function, and there are some property for the driving point impedances. So the questions may be asked, what are the necessary conditions of a network function to be a driving point impedances functions? Then you have to write previous one. What are the conditions, necessary conditions for a network function to be a transfer function? Then you have to write these properties. Once we understand the properties or necessary conditions for a driving point and transfer function, then we may able to identify whether the given network functions are driving point impedances function or not. So look one by one. This we can see this is the negative coefficient. So numerator and denominator polynomial having the negative coefficients. So this is not a driving point. This is not driving point. Here we also can see that negative coefficients, so not driving point impedances function. Here we can see that it can be written as s to the power 4 plus s square. We can write s square plus 1. So multiple zeros at s is equal to 0. So it is also not. Then look at here. Here you can see that S square S, and here we can have the S0. Look at here, SQ, S square, and here it is S0. So here S term is missing. S term is missing. S term is missing. So it is also not a driving point. So A, B, we have seen that A, B, C, D, they are not the driving point immitance functions. So look at the fifth one. Fs is S plus 1. So degrees of this is 1, this is 2, so difference is 1. Okay. 0, 0. Then it is S square S, S0. So all the terms are present. Coefficients are real and positive. So this is it. This is your driving point immitance functions. So out of these 5, 4 are not driving point immitance functions, whereas fifth one is the driving point immitance functions. So now I stop here, and in the next video lecture we will start with the steady state response from the pole 0 plots. So what we have learned here, what is poles and 0, what is the concept of poles and 0. So what are the poles and 0? Poles and zeros are the complex frequencies of network functions, and the poles determine the time variation of the response, whereas the zeros determine the magnitude of the response. Then we also discuss the location of restrictions on the location of poles and zeros in case of the network function, and that decides whether the given network function is either driving point immitance function or transfer function. So in the next lecture we will discuss the how we will get steady state response or sinusoidal response from the pole 0 plot. So thank you very much. Jai Hind.